The BMW Group plant in Spartanburg, South Carolina, is the global production hub for the X family SAV, sports activity vehicles, including the BMW X5 and its modular production variants. With an annual production rate projected to exceed 400,000 units at full capacity, the plant combines the flexibility of the modular platform with an unprecedented level of automation and digitalization. The plant has a covered area of approximately 10 million square feet, approximately 930,000 square meters, and includes 1 stamping shop, 3 body shops, 2 paint shops, 2 assembly halls, several integrated logistics centers. The core of the industrial strategy lies in the advanced implementation of lean production, integrated with advanced robotics and physical AI, physical artificial intelligence. The primary objective is to radically eliminate the 3 major wastes of lean manufacturing: MUDA, wasted resources, time and motion; MURI, overloads and operational stress on machines and operators; and MURA, irregularities and fluctuations in workflows. To address production optimization and cost reduction, lean production and Six Sigma methodologies represent 2 sides of the same coin in continuous improvement, addressing inefficiency with complementary philosophies. Lean production focuses on fluidity of flow and the rapid elimination of operational waste by addressing the 3 M's: Mura, MUDA, and MURI. Six Sigma focuses on quality stability and precision. It reduces the variability of statistical processes to eliminate defects at the root, ensuring that output strictly adheres to customer specifications and tolerance margins. Ultimately, where lean works to streamline processes by eliminating waste and overhead, Six Sigma intervenes to secure quality by reducing variability and eliminating defects. Spartanburg's ultimate goal remains perfectly integrated, maximizing overall efficiency, quality, and the economic sustainability of production. In the sheet metal cutting and press forming department, the reduction in MUDA, MURI, and MURA is linked to optimized format changeovers, robotic quality control, and reduced wear compared to traditional presses. The raw sheet metal handling process is 100% robotized, with artificial intelligence systems that monitor the quality of laser cutting and stamping in real time, autonomously correcting pressure parameters and compensating for springback of the innovative materials used in the X5 modular platform. Compared to traditional factories, the stamping and sheet metal cutting department handles tons of high-strength steel and aluminum for the modular frames. The reduction in MUDA, setup times, and material waste can be quantified at 50%. The reduction in MURI, mechanical stress and unplanned wear, can be quantified at 45%. The reduction in MURA, batch inhomogeneity and dimensional variability, can be quantified at 60%. Compared to traditional welding departments at the Spartanburg body shop, the lean reduction boasts nearly 100% robotization for body assembly. In traditional factories, the manual insertion of small sheet metal reinforcements and mixed welding posed enormous ergonomic risks. The pioneering use of humanoid robots, already employed in previous successful trials, has eliminated the critical issues of heavy handling. The welding line's flexibility for modular production is managed by predictive and adaptive artificial intelligence. The anthropomorphic robots instantly recognize chassis geometry variations, wheelbase, all-wheel or rear-wheel drive, and adapt resistance or laser welding programs seamlessly to meet the set tack time required to meet customer demand. The advantages of robotic welding can be summarized in the following 4 points: millimeter precision and repeatability. High-precision industrial robots perform thousands of welding spots per vehicle, approximately 6,000 spots, with consistent repeatability, eliminating human variability and ensuring identical structural quality on every vehicle. Advanced material management. The BMW X5 body uses ultra-high-strength steels and mixed alloys to maximize crash safety. Robotic technology allows for the perfect calibration of parameters such as heat input and pressure, which are essential for maintaining the mechanical properties of these materials. Integration with flexible manufacturing, BMW iFactory philosophy. The lines are designed to handle multiple variants and engines in real time on the same assembly line. Digitally programmed robots recognize the model in transit via the manufacturing execution system, instantly adapting work cycles. Ergonomics and safety. Automating heavy or repetitive processes protects the health of workers, who are now supported in Spartanburg by advanced support technologies and physical/humanoid robotics for handling sheet metal. To ensure high-quality standards and structural compliance of the body, production adopts a multi-level control system with real-time monitoring of electrical parameters. The current, voltage, and pressure of the welding machines are monitored instantaneously throughout the joint. Any anomalies are immediately stopped or reported to the station. Furthermore, BMW uses quality control platforms based on artificial intelligence and advanced optical/acoustic sensors to analyze the status of the work and surface compliance. Three-dimensional optical measurement technologies are used to verify that the geometric tolerances of moving and fixed parts are within tenths of a millimeter. In this department, the reduction in MUDA, dead cycle times and rework, is approximately 70% compared to traditional welding. The reduction in MURI, extreme ergonomic strain on the operator, is approximately 90%. The reduction in MURA, inconsistent welding rhythms, is 75%. Painting requires absolute precision to avoid paint waste and emissions. Compared to older systems, the use of intelligent electrostatic atomizers and sealing robots has dramatically reduced inefficiencies. Roboticization and the integration of artificial intelligence analyze the thickness of the applied film and the ambient humidity in real time, adjusting the paint viscosity and the trajectory of the robotic arms to eliminate the need for subsequent manual corrections. The reduction in MUDA in painting compared to traditional manual painting systems, chemical waste and energy consumption, is 40%. The reduction in MURI, forced thermal cycles and overloading of filtration systems, is 35%. The reduction in MURA, batch surface defects, is approximately 50%. The fifth-generation BMW X5 2027 represents a turning point in the automotive landscape, introducing an approach in which design and industrial feasibility were developed simultaneously through concurrent engineering design activities. Product and industrial engineers worked from the early digital design stages using 3 DCAD systems on a highly flexible architecture concept, using design for X procedures, such as design for assembly, design for testability, standardization, and simplification. The platform is designed to accommodate multiple propulsion variants: petrol mild hybrid, plug-in hybrid, 100% electric BEV with the new iX5, and hydrogen fuel cell, within the same basic structure, without compromising safety standards, onboard space, or dynamic performance. The first fundamental pillar was the standardization of the anchoring points, which feature universal interfaces for integrating either high-voltage battery packs with 6th-generation cylindrical cells, or traditional exhaust systems and fuel tanks. The second key point was the reduction of geometric complexity with fewer unique components and a significant reduction in raw body variants to simplify internal logistics within the plant. Waste reduction compared to traditional factories comes at this stage from the inclusion and programming of reconfigurable ergonomic workstations and the assistance of collaborative and humanoid robots, physical AI. The final assembly, that is, the interface between the powertrain, whether internal combustion, hybrid or electric with cell-to-pack technology, and the body, occurs via ultra-precise optical laser positioning stations, managed by artificial intelligence to compensate for millimetric tolerances. The reduction in MUDA, micro-movements searching for components and waiting, in this plant thanks to hybrid robotic and human assembly is 55%. The reduction in MURI, musculoskeletal fatigue of workers during underbody or passenger compartment operations, is 70%. The reduction in MURA, unbalanced station times along the mixed line, is approximately 60%. In conventional automotive plants, logistics and warehousing have historically been plagued by massive MUDAs related to manual handling of components, MURI, mutilation, caused by repetitive lifting of loads by operators, and MURA, mutilation, caused by irregular supply flows to assembly lines. In Spartanburg, the introduction of automated guided vehicles, AGVCs, intelligent logistics trains, and the advanced use of next-generation humanoid robots for picking and sequencing components from bulk containers has revolutionized the department. Spartanburg's modular logistics uses algorithms to manage the complex sequencing of components destined for the mixed line of the BMW X5 and other modular models. Humanoid robots equipped with handheld cameras and tactile sensors recognize random objects within containers, picking them up and placing them into sequencing trolleys with an adaptive precision impossible with traditional fixed systems. Humanoid robotization in Spartanburg is not aimed at replacing labor, but rather at human-machine synergy. Intelligent humanoid robots perform arduous and repetitive tasks, while human operators focus on high-value activities, quality control, and supervision of complex systems, protected from injury and adverse ergonomic loads. Analyzing the use of human resources and full-time equivalents, FTEs, at the BMW Spartanburg plant in relation to the robotic production of the X5 model compared to a traditional line offers a fascinating perspective on industrial transformation. It's not simply a matter of replacing labor with robots, but of redefining the role of the human operator through the advanced concept of the smart factory. In a traditional automotive assembly line, the use of FTEs is heavily concentrated on manual and repetitive tasks. Managing production volumes requires a large presence of workers along the workstations for direct assembly, screwing, wiring, and visual quality control. This approach results in a high physical fatigue curve for workers, frequent need for close shifts to prevent musculoskeletal disorders, and increased exposure to bottlenecks related to human fatigue or variable manual cycle times. From a human resources perspective, management requires high training turnover for new hires and a very rigid and numerous hierarchical supervisory structure. At the Spartanburg plant, the introduction of advanced technologies, artificial intelligence, and robotics for the production of the BMW X5 radically transforms the FTE paradigm. Robotic automation and the use of intelligent systems relieve operators of the most demanding, repetitive, or ergonomically critical tasks. The number of hours worked does not disappear, but shifts. FTS are decreasing in direct manual activities, but are increasing or specializing in predictive maintenance, advanced programming, supervision of robotic systems, and real-time data analysis. Thanks to the integration of flexible robotic cells, the Spartanburg line can handle multiple X5 engine and trim variants on the same line, without having to constantly reconfigure the workforce or slow down production. Artificial vision and artificial intelligence systems support workers by instantly identifying defects. This reduces time wasted on end-of-line rework and allows operators to focus their energies on solving complex problems rather than simply performing routine inspections. In short, while a traditional plant relies almost exclusively on the linear addition of workforce and additional shifts to scale production, the Spartanburg Robotic Plant decouples volume growth from the linear growth of direct FTEs. The result is a higher value deployment of human resources, where technology acts as a multiplier of human capabilities, ensuring significantly higher standards of productivity and ergonomics. The reduction in logistics MUDA, unnecessary movements and waiting times, is quantifiable at 65% compared to a traditional warehouse. The reduction in logistics walls, physical overload, and ergonomic stress is quantifiable at 80%. The reduction in logistics walls, inventory fluctuations, and bottlenecks in just-in-sequence flows is quantifiable at 55%. The implementation of these advanced technologies and the expansion of production capacity at the Spartanburg plant are part of the BMW Group's massive strategic investment plans, worth several $billion overall for the modernization of plants dedicated to the X-range and modular architectures. Non-recurring costs include the purchase and customization of next-generation industrial robots, the development of physical AI and neural network software for humanoid robots, the redesign of 5G wireless communication infrastructure, and the reconfiguration of the stamping, welding, and logistics departments. Recurring costs relate to AI-based predictive maintenance, continuous updating of machine learning models, optimized energy consumption, and specialized training of technical personnel to supervise robotic systems. The increase in overall operational efficiency and the reduction in scrap and rework rates generate direct operating cost savings estimated at between 15% and 25% compared to an equivalent traditional plant. The return on investment for robotic cells and applied artificial intelligence systems is expected to be between 3 and 4 years. The economic break-even point of the entire advanced automation project for the BMW X5 modular lines is being reached earlier than historical automotive benchmarks, thanks to the rapid saturation of the annual production rate and the intrinsic flexibility that reduces plant downtime costs for model changeovers and the drastic reduction in waste, non-value-added production time.